The title of my presentation today is Fluvial Connectivity of a Deep-Seated Landslide to Upstream Tree Harvests. And I'm going to go over sort of the failure history of a landslide relative to timber harvest activities. The landslide is located in the Clearwater River watershed, so that's pretty close to us here. There it is. It's an extremely slow-moving bedrock landslide. It's so slow that it's not really disturbing the vegetation. So if you look at that air photo, you're not going to make it out. But with the higher resolution topography data that we have today, you can see it in the DEM. It's located in this small watershed. This is East Fork Coonmanass Creek. And sort of the hypothesis of the study is that by harvesting on and upslope of the landslide, activity or the landslide may have been reactivated. So before I get into the study, I'll give a little bit more background about the sort of the tectonic setting of this area, because you sort of need a frame of reference for processes that naturally occur here. So here we are, right on the edge of the North American continent. You have oceanic crust that's moving east, continental crust that's moving west. That oceanic crust, as it moves west or east, is subducting, and all of the sediments, the gravels, the sands that have been deposited on this crust are getting accreted and are slowly building out the westward coast of the North American continent. This has been going on for millions of years, and through that process, multiple terrains have been built up along the coast. Here in where we do forestry in North America, there's sort of two terrains that really are key to the geology. The first is the Coast Range terrain. Second is the Cascadia Wedge. Cascadia Wedge is that's the terrain that's getting formed right now. That's the terrain that's you can see it's building out into the ocean. And up along the coast, there's only really one spot where it's exposed severely, and that's up here on the Olympic Peninsula, the Olympics. And the reason it's exposed severely has to do with uplift rates. They're exceptionally high right here. So let's take a close-up look at the Olympic Peninsula. So again, you have the Coast Range terrain and then the Olympic subduction complex. And there's the oceanic plate. It's the Juan de Fuca plate. It's moving east and subducting. And all those sediments are getting uplift, compacted, stressed, strained, and forming rock. As a consequence of that uplift, erosion is also exceptionally high. And if erosion wasn't so high, the Coast Range terrain, the CRT, would cover the Olympic Peninsula. But as a result of that rapid uplift and rapid erosion, it's been removed. Did you guys see that graphic? Okay. It's been removed. So the OSC is exposed, and our basin is right in the middle of where that erosion is happening. And that erosion is happening by glaciers, landslides, and debris flows. So these are processes that occur naturally and frequently in response to the tectonic activity in the area. So let's zoom into the basin and take a close-up look at the geology there. You have the more recent glacial and alluvial deposits in the Hoh River and the Clearwater River valleys, but the basin and where the landslide is right in the Olympic subduction complex, right in that weak eroding rock. Maybe it's low on batteries. Okay, if we go to the field and look at cut banks, this is what the rock looks. It's densely fractured, thick beds of sandstone and siltstone that's been offset. You also have these thin beds of sand and siltstone that are folded. And then all around you have slick and slides, which is evidence of rock under high pressure moving against rock. So that all sort of supports that tectonic setting of those sediments being uplift compacted and a really weak bedrock setting. If we go to the basin, again in the channel, bedrock is exposed and you find pockets of really weak fractured rock. There's also evidence of debris flows in the channel. And then there's landslides. The deep-seated landslide of the study is right here. And here's the basin outlet. In terms of longitudinal position, it's right about 1,700, 1,800 meters. This is standing right next to the landslide at the base of it where it touches the stream, looking downstream. Again, here's that longitudinal position. In terms of debris flow processes, you have sort of the initiation zone where debris flows start up in the headwaters. Then you have the scour section where those debris flows are sort of flushing down the channel. And then you have the deposition section down at the base where the debris flows settle. The landslide is located right in the scour section. And you can see looking at the toe, you have the conifers higher upslope, and then at about 3 meters height above the channel base, you've got this younger growth of alders, which is evidence of either floods or debris flows that have scoured and kept the conifers from establishing. Did I hit it? Okay, sorry. Okay, so that's the setting that we're in. We've got rapid uplift, weak bedrock, and erosion, and on top of that you add humans, which for the last 100 years or so have been messing with the surface vegetation. And that brings us back to the hypothesis that by removing vegetation on and upslope of the landslide, they may have triggered landslide activity. So to investigate this hypothesis, I look at it sort of involves two steps. One is what processes are triggering the activity, and two, how does harvest affect each process? So first, we just want to know what processes are capable of triggering the activity, and to do that, we use a slope stability model. We just look at 2 triggers: soil water, which is just precipitation going into the landslide, and scour. If you remove material from the toe of the landslide, will that trigger instability? And the results of the modeling show that in both cases it is sensitive. So both of those are possible triggers, just physically. The next step is to see which of those processes actually coincide with landslide activity. We don't have an actual record of when that landslide is moved, so we have to develop that. And to get the periods of when the landslide is moved, we use the vegetation growing on the landslide. So we're coring trees that are on active parts of the landslide, tension cracks or shallow landslides on the toe. And from growth disturbances that you get from the trees, we get 3 years of landslide activity, 1998 to 1999, 2003 to 2004, and 2009. So with the periods of landslide activity, now we want to relate those to the different processes. Which processes actually coincide with landslide activity? Looking at the debris flow record, from the air photo record, you can see there's a little bit of debris flows in the 60s and but then in the 90s it really picks up, and this is the age of those alders when they germinated, and they really pick up in the late 90s and the 2000s. And those periods coincide with the periods of landslide activity, so that supports the notion that debris flows may be one of the triggers of the landslide. Now comparing that landslide activity record to floods. Are there any big floods during those periods of landslide activity? There's one flood. There's a 25-year flood that occurs during one period of landslide activity. Looking at soil water, and for soil water, we're inferring that from water input, which is the rain and snowmelt that's going into the landslide. Are there any big bursts of soil water? There are 2 periods. In 1998, 1999, you get an almost 10-year event, and then later in 2009 that coincide with landslide activity. So the slope stability modeling shows that the landslide is sensitive to both soil water and scour at the toe. And then all of the processes that we looked at, debris flows, floods, and increases in soil water, they coincide with at least one period of landslide activity. So all of them could possibly be triggering the landslide. This hasn't ruled out any of them. So the next step in this is to identify how removing trees may have affected those. So the first is how did harvest affect the floods? And for that, we're using a model. And for the model to be predictive of anything in the basin, it has to be calibrated to flow data. And that's where the OASF long-term monitoring project really comes into play. We use 3 years of data from that project to calibrate the model. And here we're looking at the basin outlet. There's 3 things here that are being used. You have this location here, that's where we're measuring discharge. You have staff gauge here, we're actually getting the height of the water. And then in this tube, there's a pressure transducer that's recording the continuous record of stage height. So from those, we're developing an empirical relationship to stage height and discharge. This is a plot of that empirical relationship. And you'll notice there's several curves. And that has to do with the channel bed. This is a picture underwater looking at the staff gauge. And the channels in the OASF and Olympic Peninsula are extremely mobile. So this is an issue that we're constantly dealing with and figuring out initial methods on how to deal with. But these algae-covered rocks are rocks that have been there for a while. These gravels and sands that don't have algae, this photo was taken this winter, have just been deposited. So each time you have that rock that's being deposited or scoured, it affects that relationship that we're using to get discharge. But we're figuring out methods to deal with this. And from that, we get a continuous record of flow, a hydrograph. This is the 3-year hydrograph for that basin. The flow model is calibrated to that. Once it's calibrated, then we can use it to predict how removing trees might affect flow. And to do that with the calibrated model, we have a 67-year record of precipitation and temperature that we input into that calibrated model. That gives us flow results for fully forested conditions. The model also has parameters for vegetation, so we remove the vegetation, then rerun it for that 67 years, and that gives us another 67-year record of flow for fully harvested conditions. So here's the summary of that. So this is comparing those 2 different 67-year long records. In this plot, down at the bottom, you have the return period of the storm. Up here, you have the flow magnitude. So, for example, you have the 1-year event has a flow of about 100 millimeters per day. You also have the 10-year event and the 100-year event. This red line is for fully harvested conditions. The blue line is for forested conditions. Now you notice that the red line is higher than the blue line up to about the 1.1-year event. So the results of the model are that peak flows are affected by harvesting up to about the 1.1-year event. Beyond that, there's no difference. So what does that mean in terms of our landslide? If you remember from the flow record, it was that 1 year that a flood coincided with landslide activity was a 25-year event. That's over here. That's in that range that harvesting isn't affecting floods. So if that landslide was triggered by a flood, it would have happened naturally, which sort of fits the condition of the Olympic Peninsula. It's an area of natural landslides, where landslides and relief flows are occurring naturally. Now we want to understand how harvest affects soil water. And again, for this, we're using a model that's also calibrated and then run for 67 years. And we compare both forested and harvested conditions. And comparing that to those 2 time series, we look at how does the 30-day accumulated water input get affected by harvesting. And the result of that comparison is it is increased. Harvesting does increase the accumulated 30-day water input into the basin. But sort of an important note here is, so again, in these models, they're pretty simple. We're just comparing fully forested to fully harvested conditions. But in that basin, after they harvested, they planted. And if you remember from the comparison of landslide activity to water input, it was, I think, 1998 is when water input lined up with landslide activity. The plantation there was already close to 20 years old. So this result on water input it's really only representative of right after you harvest. So that may not represent, it may not indicate that harvesting had any effect on whether or not that landslide moved. It also might have naturally occurred. because we're so long after the harvest and trees have reestablished. So now we'll look at harvest effect on debris flows. And with this, we're just looking at the years of harvest relative to the years of debris flows. So up here in this plot, these are the years of harvest. In 1967, they harvested just the top of the basin. In the 70s and the early 80s is when they harvested the lower part of the basin and actually on the landslide. And in the 90s is when they harvest the headwaters. Now, if we look at the debris flow activity, there's just a little bit in the 60s again, and then debris flows that rapidly increase in the 90s right after they harvest the headwaters. That alone doesn't mean that the harvest might have caused the debris flows, because debris flows are triggered by precipitation. So let's look at the precipitation record. You've got big peaks almost up to a 25-year event here, and then once you get into the 90s, it actually drops or does not increase. So that in combination with the timing of the increase in debris flows, the lack of an increase in precipitation would suggest that that timber harvest may have triggered those debris flows. Also, effective cohesion is known to be reduced, where effective cohesion is the strength to soil that's added by roots. It's known to be reduced for up to about 22 years after you harvest. This is in that window. We're within that 22-year window of when effective cohesion might have been reduced by the harvest. So debris flows, they lined up with all periods of landslide activity. This suggests that if debris flows triggered that landslide, because their frequency was increased by the harvest may have triggered the landslide. So in conclusion, debris flows and landslides, I mean, they're a natural phenomenon that's occurring in response to rapid tectonic uplift. These are occurring here anyway. Peat flows, it may have been a trigger, but because it was a 25-year event, which was beyond what timber harvest is affecting, that was probably a natural occurrence. Poor water, it may have been a trigger, but because that plantation was so reestablished by the time that it happened, that probably also would have occurred naturally. Debris flows, on the other hand, they may have been affected with harvest, and there is evidence to support that they triggered that landslide. So harvest in the headwaters may have in turn triggered that landslide. And just one final note on why that might have occurred. It has to do with the position of the landslide relative to those debris flow processes. Again, you have deposition, scour, and initiation in the landslide. It's in that scour section of debris flows. If it was located down here in the deposition, timber harvests, they could have triggered debris flows in the headwaters, and they might have deposited here, the landslide wouldn't have been affected. So the landslide's really only sensitive to debris flows caused by timber harvest because of its channel location.